Let's recap. What did we learn in continuous? Name me one thing. Josh, can you win? It is not discrete and therefore it is what? But what does continuous mean? Give me an example. Good. So not discrete, so it's uncountable. Not discrete, it is uncountable. An example is height. What else is there, David? Someone else. Jack. Time. What else? Frankie. Weight. What else? Jonathan. Oh, you could argue age. Age could be, yes. Depends if you count the days and months and minutes with it. So that hence it falls under time. So age, got speed, you got temperature. Anything that is not something where you can count is a singular term. Like remember those t-shirt sizes, small, medium, large. Shoe sizes, 12, 12 and a half, 13. Unless you get very specific shoes, okay? Somehow, it's like unless you're buying a shirt and you're getting a tailor-made, then that's when it's continuous. Whereas if you're just buying a shirt off the shelf, that's discrete, yeah? So this is continuous. Then what do we learn about being continuous? One of the things that we know. So we know that these are the possible variables you can have. What happens if I want to measure the percentage or probability of choosing someone who is, if I'm measuring height or time or weight or age or speed or temperature, there had to be a way to solve this. And the key word or the key thing that we have to look for. What are you looking for? What are we looking for, Percy? In order to do continuous random variable, what do we need? You need a function. Okay, now this function, because we can't find the probability like we normally do, we can't say, well, if it's, let's say, rolling a dice, it was 1, 2, 3, 4, 5, or 6, you can tell me already the chance of getting a 6. You say, well, there's 6 options, and there's only one of them, so you say it's 1 out of 6. The problem with continuous or continuous variable height, time, and weight, and age, and speed, you can't choose one instance. You can't choose a particular time or spot. You can't say, what's the chances of someone, I don't know, getting to school exactly on, I don't know, 8 a.m. We don't know. We don't know what the probability is. There could be 1 out of, like, well, you could come here at 7:59 and 59 seconds. You know, you could come here at 7:59 and 58 seconds. So how do you work out that probability, 1 out of 1? Whereas finding 1, 2, 3, 4, 5, 6, the outcome was very clear. It was out of 6. And you say it's 1 out of 6. But you can find continuous if you did it between a region. If the time, let's say, starting school was from 8 a.m. to 3 p.m., I'm just making it short and easy, 8 a.m. to 3 p.m., okay? Then you can work out the number of hours between that. From 8 a.m. to 3 p.m., that's a total of, what's that, 4 plus 3, no? 4 plus 3, 7, yeah? 7 hours. That's a total of 7 hours. So if I asked you, what's the chances of finding a student who comes to school between 8 a.m. to 9 a.m., okay? You can now say that's 1 hour. 1 out of what? 1 out of the 7. So now that's the chances. You can find that out. You can find the percentage of that hour. See, that's possible to do now. But why was it possible? Because you're working between a region. See the difference? Whereas discrete, you didn't have to work out a region. It was just, you got 6 outcomes, it's 1 out of 6. That was really easy to do. Whereas continuous, when it comes to speed, temperature, we can't choose one particular instance. That's why we have to work with regions. And so once we know that we have to work with regions, back to what Percy said, the only way to work with regions, we can say, well, if we can find a function to model a probability situation, which this is what we want. We want a function where we can talk about a region. So I'm going to write here region. We want to talk about a region or interval. Then in a function, region can represent, if this is the region, so if I say 8 a.m. to 9 a.m., then the region, which is the area, can represent my probability, can talk about a portion. And so that's why we say that the area, if it can represent, I'm going to put the word if here, if it can represent probability, we can analyze it. That's what we want. But the only way for us to say that probability is the area, it has to be what, Sebi? Not negative, good. So this is, now we're talking about a probability density function. PDF, how do you put that away? I don't even know. Oh my God. PDF, probability density function. So probability density function literally just talks about what I just described with you. That we've got a function, and if we want to find the interval between 8 a.m. to 9 a.m., if I want to model this situation from 8 to 3, for it to be a probability, it has to all add up to 1. Okay, like a probability, for that to work, it has to be a probability density function. That's all it's saying. It's just saying if this works. If it doesn't, it's not PDF. But if it does, we give it a special name. We call it a probability density function. And yes, Sebi, you were right. Number one, it has to be not negative, which we say the curve is above the x-axis. Or two, we know that the sum of all the probabilities, so imagine the curve, if it carried on all the way to, let's say 3 p.m. was all the way here, then I know the area, that's 7 hours there. If I want to know from 8 a.m. to 9 a.m., that's a portion. That's a portion of the 3. This whole area, the probability altogether, that's 1/7, 1/7 plus 1/7 plus 1/7, all the way up to 3. It has to equal to 1. That's why they say there's 2 conditions here. F of x has to be greater than 0, or equal to 0, or the sum, which means the integration, the area under the curve, negative infinity to infinity, of the curve has to equal to 1. Does that make sense? Does that link to what we're trying to say, what we're trying to describe? Yeah? So what we're trying to say is the region is what we want to work out, but in order to model this, we need a curve to fit these criteria. Okay? And those criteria make sense. So let's talk about the criteria again. This one makes sense. Area under the curve. If it is the probability, it's a region. It makes sense that the sum of all the areas has to equal to 1. Why does the curve have to be above the x-axis? Why is that? Someone describe that to me. Amir? Why does the curve have to be above the x-axis? What can't be negative? The probability, which is represented by the area. See, if you have a curve under the x-axis, which is key, if the curve is under the x-axis, the area under that curve, you would say it's here. But that area, you would call it negative area. That would imply that negative area would be negative probability, which doesn't make sense in our case. We can't represent that. We can't say, oh yeah, that's now negative 50%. What does that mean to us? It doesn't mean anything. We only know it's 0 to 100%. 0% to 100% is our chances. Yeah? So that's why you can't have a curve below the x-axis, because then you have a negative area. If you have negative area, you have negative probability. That's why it doesn't work. How do we feel? That makes sense? Good, because that's all I'm going to revise for today. You've got your expected value variance from chapter 15, but we're going to use this concept to understand chapter 16. Okay, so chapter 16 relies on this understanding that it's a probability density function, and it has these 2 conditions. Easy? All right, let's have a look at chapter 16 now. Let's go, chapter 16. Why does it look like that? How do I close this? Hold on a second, let me just close that. Oh no, I don't want that bar. How do I hide this bar? Oh. I don't know. Oh well. Let's try to stick with this. Normal distribution. Chapter 16. Normal distribution is what we call like a bell curve. It looks like a bell shape, right? They say that the probability density function of a normal probability distribution, there's massive words for all it's trying to say, is this curve, this bell curve that you see, is a probability density function. What does that mean? That means that this function, remember I said it could be any curve. It could be any curve you like. And it just happens to be that this symmetrical curve, okay, has an equation which I'll show you later. That means that this curve, 1, it's above the x-axis. 2, the area under the curve actually sums up to 1. Now why do we like this? And why are you studying this? You're studying this because someone wanted this. They figured out the curve. So remember I said before, just now, I said, oh no, oh, it doesn't stick. This happens every now and then, it gets miscalibrated. So now you're just going to have to look at my board. I'm going to do my, I know, it won't be recorded, you only hear my voice while I talk. But here we go. Remember I just said before that you could have any curve you like, and I kept doing that curve, right? But as long as it fits two conditions. If the curve is above the x-axis, and if the area under the curve adds up to 1, we can use this to model the probability or situation, right? Then, in this case, someone figured out, got a name, the person figured out the curve, and this is the curve that they've given. Okay, you don't have to memorize this curve, but I'll describe it later. They figured out this curve, f of x. You type that in your calculator, you will actually get this. It's a bell curve. And they've figured it out such that this will give you 1, the condition is it's above the x-axis. 2, the area from negative infinity all the way to infinity will equal to 1. So it's a probability density function. Why do they like this? Because when they designed this, it is not only symmetrical, so that's key, symmetrical. Why do you want to know if it's symmetrical? Because that means if the whole entire area equals to 1, that means this entire side here has to be 0.5. That means the area on this other side has to also be 0.5. Okay? If it's symmetrical, that means if this is 1, this is negative 1. This is nice. Okay, this is nice because now you can calculate things. You can say, if a situation happens to be a bell curve, which is what we try to do with your donuts. See, we're trying to say, where's your mean? Where's your average? And where's the top end, like the top 5% of the state? And where's the lower end? Where's the lower end of the, it's not top end, bottom end of the 5%, okay? So, that's how, the bell curve is a nice thing. If we can make our data become a nice normal distribution, it's easy to calculate. Because we can calculate the median is the 50th percent, or the average, we can work out where the average and the median is, and above the average, okay? This is what we want. So the first thing you need to understand is continuous is chapter 15. An example of continuous is chapter 16. That means everything you learned in chapter 15, how to find the expected value, how to find the variance, applies to this as well. Because it's the area of the curve, right? Now what they say here is, this is a normal distribution, which is the name for it. It's a bell curve. It's a probability density function. It has, and the special thing it has is the mean is at 0. Mean is 0. Okay, so the expected value is 0. And the standard deviation is 1. Standard deviation is 1. So if you remember this property I gave you, do you remember at the very start of chapter 13, there was one time where I mentioned about your probability of x, where you have the mean add 2 standard deviations, and the mean minus 2 standard deviations, and 2 standard deviations in one here. Not that, yeah. 2 standard deviation equals to 0.95. You guys remember that? In this chapter, you're going to see how relevant or how useful knowing that property is. Okay, so all this is saying is, wherever your mean is, so our mean is at 0, if you add 2 standard deviations to the right, and if you minus 2 standard deviations to the left, so this is 1, that's 2, 2 standard deviations to the left, what we can say is this area will be approximately 95% of the data. Okay? And there's going to be a few more problems you're going to learn. You're going to learn the 68%, you're going to learn the 95 and 99.5. Okay? And that's what we're going to try to work with, and that's how you can solve problems. That's what chapter 16 is about. Okay? And it's easy once you link it all together. It's the same thing. Whatever you learn in chapter 15, you're using in chapter 16. Okay? Now, so what am I trying to say out of all this? I'm just trying to say, from chapter 15, we want a probability density function. They found a curve for that. And this particular curve is a perfect curve. It's a symmetrical curve, and because it's symmetrical, it means it's easier to solve. But that's all you have to understand. This here, this mumble jumble, you don't have to memorize that, they'll give it to you, okay? This curve is a bell curve, and all you need to understand is this fits all the criteria for a probability density function. That's it, okay? All right, now let's work on working with this nice graph to what we were going to do in this exercise or this chapter. So this is a normal distribution. The other name for it is the standard normal is the other name. Okay, so if you can write on the side, when they say standard normal, this graph, for texture, this is also known, aka standard normal. So if you look in the exams, if they ever say standard normal, they're implying this. They're implying it's this curve where the mean is 0 and the standard deviation is 1. That's what they're trying to say. So if in your exams, if they ever say you've got a standard normal graph, that's what they're trying to say. Okay? Now, if this is your curve, then there's a couple of things that you can learn from this. You can talk about dilation, translation, all the transformation skills you've learned. See, this is what you're affecting your x values. Remember, what you're affecting your x values determines whether you move left or right. True? The thing that you're multiplying to it, in this case, it's multiplied by 1 out of sigma, or 1 out of standard deviation. And this is your dilation factor as well. From the x-axis, dilation from the y-axis. Translations, and this reflection. Yeah? Now, what you can see here is they're trying to describe the transformation. They're saying it is dilated by sigma, okay, and it's translated by mu, which is your expected value over sigma, but if you cancel them out, it becomes mu. Okay. So what I'm trying to say is this is your left or right. That's what your x coordinates are. And here is your y transformation. There's no vertical translations. You can see there's no vertical translation. It's not plus d or plus anything. This is your dilation, hence y. Okay? So that's a constant, this is your dilation, that varies. We cool? Okay, so I'm just talking about what that is describing. And this here says this is the translation of mu units or expected value units in the negative direction of the x-axis, followed by a dilation from the x, and a dilation from the y. Okay? And this here, we call it the standard normal because, I can't even write on it. They replace this x minus mu over sigma, they replace it in column z. Okay? And this is where it gets confusing for some students, and I'm going to try to describe it in the next slide. That z is just replacing this. So z is responsible for all of that, and this is your z-axis, is what they're trying to call it. Okay? Because instead of x-axis, we're calling it z-axis. Okay? I know it sounds pedantic for now, but on the next page it makes sense. Okay, so all I want you to understand is this represents, or this just changes the left and right. All they've done is they've just put z there, just to make it easier in terms of writing. Okay? Now, why is it important? Because we call them z values, and when we say z values, you're really referring to the x-axis. Now, what I want you to see, everything here makes sense. Consider the normal probability distribution. This is your mean, this is your mean, this is your mean, this is your mean, right? Area under the curve is 1, so we already know that. It's a probability density function. So when I say negative infinity to infinity, that's x, then the area under the curve, or the probability of the area, has to equal 1. True? Whereas from negative infinity up until mu, it has to be 5, so that's half. It's a nice distribution, symmetrical. So if this is if it's halving it, that's 0.5, this also has to be 0.5, right? That's what they're trying to say here. Anything less than mu is 50%. Anything greater than mu is also still 50%. Okay? So we've got this nice distribution, it's always 1, and in the center where the mu is, it's always your 50% point, or 50. Yeah? Now, if I move this, this is the key part. In reality, most of our data is not a perfect mean of 0. Okay? Our data will vary. Our data will vary. If I measured everyone's IQ right now here, we're not going to have a 0. We're not going to have a mean of 0, right? Our mean is going to be somewhere else. So that affects our graph. This is what we like. So this is our perfect graph. The problem is, in reality, you can get something like this. So you can have your 100, that's your average mean for the IQ test. And you've got 5 standard deviations across, so 5 across, 5 left. Okay, you -5, add 5, this will give you a certain amount of probability. So this is where the majority of people sit, okay? That's the probability of the occurring. So the chances of choosing someone who has an IQ between 85 and 115 is the area under this curve. Sure? So that makes sense. The problem is, how do I use this to move back to here so I can understand what my mean is and what my standard deviations are? Because we like this curve. This is the perfect curve. This is still a normal distribution, but it's not in what we like. We like it when the mean is 0 and standard deviation is 1. We love that. Okay? Because we've calculated all the probabilities. We've calculated all the probabilities for, and there is, if you check back in the days, we used to have what we call Z table. Okay? And the Z table, someone's actually sat there and calculated for every Z value, whatever is it, Z1 or Z1.1 or whatever it is, they've calculated the area under that curve. If they know the area under the curve, that means that can be called the probability. That's what we want. Because remember, you're trying to model it so you can find the probability. So in this case, we don't know what this probability is. We don't know what that is. So when I say find the probability of choosing someone, so X being someone, who has an IQ of 85 to 115, I don't know what that is. Okay, I have no idea. But what I can do is if I can translate, this is just a transformation of this curve, if I can translate what 85 represents on my z-axis, okay, then I can go back to the z-tables back in the days, I'll write here z-tables, and I can look for, if that's 85, I can work out for what it represents, because 85 could represent, let's say negative 1.2, hypothetically. Okay, let's say 85 is like negative 1.2. Then I can go back to the table and find negative 1.2, where it's less than that, and I'll find out what the area is. And I'll tell you, because someone's already calculated that. They spent all their time to calculate this curve. That's the only curve that we had. And it was nice because the mean was 0 and the standard deviation was 1. You go over here, the mean's different, and the standard deviation is different. We don't know the area for that. We have no idea. But if I can translate this curve back to this, I can say, what is 85 as my z value? What is my 115 as my z value? Then I'm on the ball. See, I'm on the ball. If this was negative 1.2, this would have to be 1.2. Okay? And then I can now find the area between negative 1.2 to 1.2. That will be exactly the same area. That's just because both of them have the same chances. Okay? So what we're trying to learn to do in this exercise is how to read or how to transform 85 back to the z value and 115 back to the z value. And that's what that previous slide was about. So what I gave you here. This says whatever your data was, minus whatever your mean was, divided by the standard deviation, which really is just the transformation. You're just working backwards. So if I move to the right by 3, then I'm going to subtract and move back to the left by 3. So if I'm cross by 3, I subtract 3 to get back. Whatever the mean is, I subtract the mean, so I move it back. So if you think about it like this, and this graph here, if my mean currently is 100, I just take, if I want to make it move it back to 0, then all I have to do is say, take 100, which is my x, minus my mean is 100, of course, it's going to be 0. It's going to bring it back to 0. It doesn't matter what the standard deviation is. So I've just changed this 100 and moved it back here. But not only that, there's a difference. This one's thinner. This one has a dilation. And that's why you have to also account what the dilation is. Okay? So the formula, if I wanted to change 85 back to a z value, this is called the z-axis, the z values. I want to know what it corresponds to. Then I would use my z idea, the transformation. I know I'm moving left, right, by mu, so x minus mu, divided by, because you're multiplying by a dilation factor, so the sigma. In our case here, we know what the mu is. Mu is 100. In our case, they haven't told us what a standard deviation is. We can assume that this is 5 across and 5 across. Okay, so it's 5 to the left and 5 to the right. And I can work that out. I can say that would be 85 minus 100 divided by 5. Okay, so assuming the standard deviation is 5, now I can work it out. 85 minus 100 gives me negative 15. Negative 15 divided by 5 is negative 3. So what does it imply? That means that my z value, this is negative 1, negative 2, negative 3 will be here. So that's corresponding to an 85. And then if that's, because it's symmetrical, if that's minus 3, and this is also plus 5, so that's plus 5 minus 5, then over here would be minus 3 plus 3. So the area from here to here, so if I write it out, probability of negative 3 z value, not x, z value from negative 3 to 3 is equivalent to the probability of 85 x to 115. Does this make sense on what we're trying to do? Okay, so this is the curve of our reality. We like this because we can find out that. We can find out the area based on z value tables. Someone who's put out the time and effort to do that. We don't know this. So we don't know for a mean of 100, standard deviation 5, we don't know what the areas are. We have no idea. But we can change this to this using that idea because we know the transformations. So I've just changed my x value, 85, and negative 3, and I can do for 115 too. So if I do 115, take away, so x, take away mu, take away 100, divided by 15, wait, not 15, 5, okay? Still works out 15 divided by 5 is 3, which is true. That's what I do. It's symmetrical, okay? So I'm trying to relate my current actual data to what they have. They only have the z table. This is the normal distribution. So they love this curve. This is the original curve. They loved it. They got all the areas and everything calculated. It's symmetrical. But they don't have this. They don't have this curve. It's symmetrical as well, but it's skewed and it's all different. And you can hear so many different types of graphs that are normal, but it's not the perfect normal. So this is called the standard normal. It's called normal distribution. So in your exams, they will tell you the difference. They'll give you a hint. They'll say, according to the standard normal, then you know this. Mu 0, standard deviation 1. But then if they don't say standard normal, you're working with a random graph. And your job is to move it back to this. But if they gave you this already, you just plug in the calculator and get your answer. See the difference between the two? Does it sort of relate what we're doing? Yeah, so we're trying to find the area under the curve, interval to an interval. We don't know what that is, but if I can translate these two intervals, that x represents the z value of negative 3. This represents z value of 3. Then if it's interval from here to here, it should be the same as the interval from here to here, providing they're both normal. If they're both not a normal curve, you can't do that. Okay, and that's why that's the assumption. That's the assumption. They always say it in your exams. They'll say, assuming you've got a normally distributed graph, find yeah, that's what they always do. Or they say, given that you have a standard normal graph, so it's like this, find Okay, so your job is just to identify two things. Do I have this graph? Or do I have this graph? Is it standard normal or is it just a normal? If you want to change a standard normal, a normal to a standard normal, it's just a transformation. Okay? That's a relationship between z values and your actual x data. We're going to do some examples so you get a good feel. Okay, so let's do some examples here. So, let's have a look. Do you need to know much of that? No, so that's what I was just describing here. That's what I was describing. Translation, no. That's moving the mean. So obviously if you move the mean across, so remember your x value, wherever your mean is, you change it. It started off with 0, if you made the mu or the expected value 10, then it moves to 10. If you made it 100, it moves to 100. Okay, that's what they're trying to say there. All right. Now, standard deviation, this makes sense here too. Standard deviation is your dilation factor. So obviously, stretching vertically. If you increase your standard deviation, if you think about it, if you increase your standard deviation, of course, your z value is going to get smaller. You can look at the graph. The larger your value, so if your transformation is like 3x, that means you're dividing it by 3, it gets smaller. That's why they're saying if this is mu2 has a greater value than flat. So if I put 3x, gets a third. If I put half x, it's going to get larger. Okay? And this just basically is a dilation from the x-axis. So if you're confused right now, go all the way back to the very beginning, right there. See, if I change that sigma, remember if it's a transformation of 3x, then this now becomes out of 3. But if it's out of 3, you shrink it. But if it's half x, then that becomes half. Effectively, it becomes twice the x value, so it gets thinner. Or technically away from the y-axis, it gets wider. Okay? That's the only reason why, and that's what that's for too. Cool? Alright, let's go back and let's do an example just so you get a good feel before the end of the session. Let's go now. Alright, here. Let's start off easy. Where's my duster? Where did I put it? Oh, here we go. Let's have a look at this question. Suppose that z is a standard normal random variable. So there you go. So that's the first part of the question. They'll tell you, is it a normal or is it a standard normal? If it's standard normal, you know one thing. It starts at mu is 0, so the expected value is 0, the mean 0, and the standard deviation is 1. That's what standard normal means. Okay, that's your normal basic graph that they started off with. Here they go. They say now, find the probability of z -1 between -1 and 2.5. So you visually try to understand this. All they're trying to say is you got a normal distribution, mean 0, standard deviation is 1. This is your z. Okay? And you're trying to find from -1 to 2.5. So -1, which is from here, to 2.5, so let's say this is 2 and that's 3, and 2.5 is around here. Your job, find that. And you don't have to go to z tables anymore, because this is already, and as a standard normal, you don't have to go through z tables. Back then I had to. Then back then I had to go back into the textbook and the appendix, and I have all these tables here, and it will have all the numbers on the left and all the numbers on the right, and I have to look for -1 to 2 so they can work out the area. Sometimes they don't even have an interval, so I have to work out less than -1, less than 2.5, and I subtracted the 2 to find the area between them. You don't have to do that anymore. Now, you literally go on your calculator and type normal distribution or normal CDF, -1 to 2.5, and then calculate it for you. You don't have to do what I used to do. Okay, so here we go. To find the probability, this is found in menu, probability distribution, normal CDF. I'll show you on the calculator as well as we do this. So if you go to menu, 5 for probability, 5 probability, and I'm going to go distributions. So menu 5, and here you've got normal PDF and normal CDF. Now because we're working with regions, remember it's a region, you never do PDF. PDF is non-existent in our case here. Okay, in our sort of understanding at year 12, we're not doing PDF. We're only going to do CDF because we're calculating the region. Okay, we're calculating from -1 to 2.5. So we're going to work with PDF, CDF, so it was menu 552. Okay, menu 552. So here we go. Our lower bound, we already know if this is calculating for mu 0, standard deviation 1. That's a standard normal graph. We've got our intervals. We already know it's in z values. Z values from -1 to what was it again? 2.5. Okay, so you just type that in. -1 to 2.5. You see, back then I had to work that out. I had to work out lower bound and upper bound, and I have to subtract the two. You know it now. You type all that in, assuming it's a z value already. You're done. So here, I go to enter. Or you could have typed norm CDF if you wanted to. -1, 2.5. That's my left bound, right bound. 0 is my mean, and that's my standard deviation. Gives me an answer at 0.83. And this is from their table, from what they've calculated. So I now know that calculates 83% of the data. Okay, so that tells me it's 83% of the data. So if I go through this, that just means in this graph here, I've drawn this area, this probability, chances of getting from -1 to 2.5 is 83%. How do we feel? Does it kind of make sense? Let's find one where it's not Z value. Okay, let's find one that's not Z value. Let's find one that's not Z value. Actually, before we do that, what about probability of Z greater than 1? That's what I want you to do. Let's have a think about this one. Greater than 1 just means this. See, if this is your Z value, that's mean is 0. Greater than 1, that's 1, you're trying to find this area. From 1 to infinity. And you can do the same thing again. Go through norm CDF 1, which is your left bound, to infinity, standard deviation 1, mean 0, I'll tell you. And that's 15.6%. Okay? Now, what I want you to also realize as well, which is what you're going to be doing in this exercise in this chapter, chapter 15, if this is 1, this is -1. Because it's symmetrical, that means this area over here, Z less than -1, is also equivalent to the probability of Z greater than 1. And that's where you're going to do some problem solving. Okay, because sometimes I'll give you this, and then expect you to find this, and you have to work it out because it's symmetrical. You can problem solve it. Okay, but that's the first thing I need you to understand: what a normal distribution is and a standard normal. You know the difference between the two. Okay, now let's try to find an example where you don't have a standard normal. So let's say this example here. Let's look at this example. Same thing. The first start of the question in your exam, the first thing I need you to see is when they say x or whatever it is normally distributed. See, they didn't say standard normal. So when they don't say standard normal, they have a different mean and they have a different standard deviation. So, what does that mean? Visualize it. Draw the graph if it helps you. I always teach my students to draw it and it makes it so much easier. Draw the graph. Mean is 100. So this is 100. Standard deviation 6. So 1 across 100 plus 6 makes it 106. 100 minus, that makes it 94. You're trying to find where x is less than equal to k, where it's 95% of the data. So 95% of the data, I need to find x. Wherever x is, x could be here, but I want that area to be 95%. How do you do that? Work backwards. There's an inverse norm on your calculator. That works backwards. If you know the area, standard deviation mean, you can solve for it. So it'll look like this. Area, mean, standard deviation. That will calculate your x value. Okay? If you want, but it only works from left to right. It only works from left to right. Just keep that in mind. Always left to right. That will tell you the x value, give you that value. Okay? We'll work on it next session, but that's 16. We'll revise it again. Thank you. Thank you. To take in. It was meant to take in.